In today's video, I want to take a look at the producer-consumer problem and what it actually is, and then how to solve it. First things first, let's get a little bit theoretical, because this problem is kind of abstract and, well, hard to understand at first. The idea of the producer-consumer problem is that we have a shared buffer, so a buffer that is in shared memory between multiple threads. Let's say like this. This is our little buffer that has a few elements. Let's say it's a simple array, and in it there are certain producers that add things to the buffer. So here we're gonna have an arrow that denotes the producer, and we're gonna have consumers that take things from the buffer, right? And these are named producers and consumers because the producer actually produces some valuable data that then is passed to that buffer, and the consumer takes in the data and also processes it some way or another. You can think of, there are many examples in real life that you're going to be able to find, but a really good one I think is if you think about requests as elements in that buffer. So requests to a server, just HTTP request. You know, when you access a website, you send a request to the server. You can say that your browser is the producer of that request, and that request is passed into to this buffer, and then the consumers of those requests are the servers themselves, where it could be one or more. Okay. Another good example would be a printer queue. So if you have one printer in an office of, like, let's say 10 people, and all 10 people want to use that printer, you're gonna have to have some mechanism that manages the order in which each print occurs, right? So in that case, the employees that use that printer are the producers for that information that needs to create the paper itself, and that information is taken from the buffer by the printer, which is our consumer in that case. Now there are at least three problems that we have to solve in the producer-consumer problem. One is that we are using shared memory, so manage shared memory access. This is what I mean by that is that the buffer is in shared memory and it's going to be accessed by multiple threads, possibly multiple producers, possibly multiple consumers, but at least one of each. So we're going to have to make sure that we don't have any race conditions in that, probably using a mutex. As the first problem. The second problem is what if you have, let's say, two producers and only one consumer, right? And let's say all of them actually produce at the same rate, right? Well, if you do that, then that means that you're gonna have many more items in the buffer than the consumer can take from it, right? So if in 1 second you're producing 2 items, the consumer can only take 1. And at one point the buffer is gonna be full. What's gonna happen if the buffer is full? What are the producers gonna do? Because they have to do something. You cannot just have a simple while loop that keeps on checking whether or not the buffer has an empty slot. We're gonna have to handle this one way or another. So this is another problem that we have to handle, that is checking for if buffer is full. And the third one is the opposite of this. If you have, for example, one producer and 2 consumers, in that case, then what happens if the consumer actually tries to take items from an empty buffer? What happens exactly? Do you actually have a while loop again that just checks? That's not that efficient. So you can solve these problems in multiple ways, depending on exactly what the problem is. But this is the problem at hand. Whenever you want to take things from that buffer, you have to make sure that there are actually something to take from. So checking for if buffer is empty. And that's all we're gonna tackle in this video. There are sure many other problems, and of course there are gonna be better ways to implement than what I do here, but this is a very simple example, and I hope you understand it through this. Now let's start by creating the actual buffer, right? That's the first step. So I'm gonna have the program simply have producers that produce random numbers, and consumers that consume the numbers and they just print it on the screen. That's all. But really, these two operations, you should think of them as something that should take a bit of computational power, right? So in that case it doesn't, but this is just for to exemplify. So now let's create a buffer. We're gonna have here an int buffer, let's say of 10 numbers, and then we're also gonna need a count, and that count should be set to 0 because we don't have anything in the buffer at the beginning, so that's fine. Now I'm gonna create one producer and one consumer using, of course, 2 threads, and it's the same code that you've seen before, so I'm just gonna fast forward through it. And just like so, we have created here thread num threads, which is right now defined just to be 2, and half of the threads using this if are going to be producers and half of them are going to be consumers. So right now we're going to have just one producer and one consumer. And of course we're joining them here at the end. Nothing fancy. Let's create those these routines in here. So void pointer producer, and we don't take any arguments, but gonna have to add those there for the signature. And the producer, what it does really is, well, first it generates a random number. Now to make sure that our random numbers are always random, I'm gonna do a srand of time of no here in the main function, and then in the producer we're gonna say, let's say int x equals rand, and say %100. So we're gonna get any number between 0 and 99, and that's perfectly fine. This is sort of the produce step, right? So the produce step is sort of separate from the synchronization step, the step where we're actually going to be adding it into the buffer. Here, we're going to add things into buffer, so add to the buffer. Well, to do so, all we have to do is just say buffer of count equals x, right? So count is gonna be, if it's 0, then buffer of 0, that's fine, it's the first one. If it's 1, then that's the second element, and so on and so forth. So that's perfect, and then we increment the count once we're done. So that's just adding to the buffer. Amazing. That's technically all you need to do. Now, for the consumer, let's see. It's kind of the reverse, right? We have first remove from the buffer. That's the step that we have to execute first. So I'm gonna have to get the element from the buffer. How do we do that? Well, we can get the last element from the buffer, which is count -1, and I'm gonna use the buffer as a stack. So it's first in, last out, but it could be implemented as a first in, first out the same way. It's exactly the same thing, except I don't want to move all the elements to the right or to the left. I just want to take the last element that has been added. That's fine. So here we take it from the buffer, and then of course we're gonna decrement count, just like that. And then lastly, we're gonna actually consume, and by consuming here we just mean printing it to the screen. That's all. So we're gonna say got a number that is y. Okay, so we have 2 threads running this. If we try to launch this, we should see something that works. Okay, so we got 69, that works. And now really the only issue with this is that the producers and the consumers are something that are usually processes that are long running. So usually you continue on producing things, so right, like your browser, if you change site, still produce requests to the servers, and servers are always there to actually accept those requests, right? So to simulate that, we're gonna create here a while loop. So I'm just gonna say a while of 1. It's never gonna finish. I'm gonna have to finish to actually kill the process in order to stop these threads, but that's fine. That's perfectly fine, especially if we don't have any dynamically allocated memory here. Now, if we try to launch this, let's see what happens. Oh, we had a segmentation fault. Why is that? Well, that's really because we are not taking into consideration the space that we've allocated for the buffer. So we only have 10 slots, 10 integers that we can store in this buffer, and if it goes past that, it doesn't really care about it. And really, this producer consumer method revolves around a bounded buffer, so a buffer that cannot grow in size. This is what it usually comes down to, but there's also implementations where you have an unbounded buffer, but that's a bit more complex. So here we do have to check if the count is a certain number, but before we do that, remember what I said when I first presented the issue. The first one was actually shared memory access. Because we are accessing the same buffer from two threads, we should stop the race conditions. So we shouldn't allow, if one thread is trying to increment count, the other thread shouldn't at the same time decrement it, right? It should wait its turn. So to do that, we're gonna have to use a mutex here. First things first. Just like that, initializing and destroying the mutex, pretty simple. And then what we have to do is just call pthread mutex lock, mutex buffer, and unlock whenever we are done modifying the actual buffer, right? Similarly here in the consumer, we're gonna have to add a lock and an unlock on this. And let me move this comment up here like that so that they are looking like the same thing. Okay, so now if we try to launch this, we are still going to get a segmentation fault like we expect. So a bit past after 10 elements, we hit a place in memory where we didn't have access to, so it just kind of broke. How do we fix that issue? Well, a naive attempt to fixing this issue is to add an if statement. So whenever our count is actually less than 10, then we can actually add to the buffer because we have space in that buffer. Otherwise, we don't add it, I guess. And similarly here, if the count is higher than 0, only then take something from the buffer. And actually what I'm gonna do here is also instantiate here a y. I'm gonna set it to -1 so that I can print it outside of the if statement. So it's gonna print -1 if nothing was taken from the buffer. All right, interesting. Now if we try to run this, we're gonna get a lot of messages printed on the screen. So this definitely works, but as you might have noticed, we got actually a lot of -1s. Here they are, right? And this tells me that there's a lot of CPU cycles wasted just basically doing nothing with getting nothing and trying to get nothing from the buffer and so on and so forth, right? Basically busy work that accomplishes nothing, because -1 means we didn't get anything from the buffer, but we still sort of consumed that. Sure, you could check it, but you cannot stop. You have to somehow not check so often that there is stuff in the buffer and sort of wait whenever there are things in the buffer. So that's a problem. And another issue that's even bigger than this is that in some cases the producer ignores certain numbers. Remember when I said that if the buffer is full, then we just keep the number. But what if that number was actually, let's say, a request to your bank account, right, that you made for a payment that was kind of important to do? Should it be just ignored? Not a good solution for this, right? So we have to find a better solution than this. And you can see here, if I put an else statement, if I say printf skipped %d\n, I'm gonna say here x. And if I try to launch this, you're gonna see a couple skipped messages here and there, actually quite a lot. Yep. Probably the buffer is very full and the consumer doesn't consume them fast enough. Yep. Okay. But we know that that still works, just not optimally. Right now we are throwing away some requests, some numbers in this case, and we are also wasting a lot of time just taking nothing from the buffer. Now you could think of many solutions to this. One of them would be to just sleep for like 1 second and try again whenever there is stuff. So if the count is less than 10, try to sleep and then try again to check if it's less than 10, and so on and so forth. That could be an idea, and with condition variables you could actually achieve this. But another idea is to use semaphores, because with this semaphores are quite valuable in that they have that value stored in it, and we can have two semaphores, one that stores the number of empty slots in the buffer and the other one that stores the number of full slots in that buffer. So let's try to implement them. Here we're gonna define two semaphores, so semT, let's say sem empty and semT sem full. Don't forget to include semaphore.h here up top, it's very important. And then let's also initialize them in our main function. So you're gonna say sem init of sem empty, and the second one is 0 because we're not sharing it between processes. We only have one process, two threads. That's fine. The value, well, for sem empty, it's kind of interesting because we have, how many slots do we have in the buffer? We have 10 slots and we have no elements in the beginning, so this should be a 10, right? This is the number of slots that we have available at the beginning. Then we can initialize the other one, sem full, and same thing, 0 as the second parameter. And the third parameter, well, we have no elements in the buffer, so no fully occupied slots, therefore we have 0 as a default, as an initial value to the semaphore. And of course we're going to destroy them once we're done using them. I'm going to say sem destroy of sem empty and sem destroy of sem full. Now if you understood what the semaphores actually represent, it's actually pretty logical the way we're going to have to use these. So we can use either sem wait to decrement the semaphore and wait if it's 0, or sem post to increment it. Which goes which though? Well, in the producer, we're gonna have to decrement before actually putting something in the buffer. So decrement and wait until there is an empty slot, right? So we're gonna sem wait on sem empty. If sem empty is 0, that means there are no slots on the semaphore, therefore we should wait here. There's no point for us going forward because there's actually no slots left for us. Okay, so that's fine. If there is, if this passes, that means that there are slots, so we can just add it. And once we're done, we should post on the sem full because we have added an element to the buffer, so we should increment the semaphore that represents the number of elements. I'm gonna say here sem full. And well, basically the same thing but in reverse for the consumer. We're gonna have to sem wait on sem full because we want to wait until there is at least one element in the buffer, right? Sem full, if sem full is 0, then this sem wait call is gonna wait until it's more than 0. So we're just gonna wait until there is actually an element in the buffer that has been posted by this producer. And lastly, of course, we should actually post on the sem empty semaphore, telling everybody that's waiting on the semaphore that, oh, now there's an empty slot in the semaphore because we have taken something from it. So you can say here sem post on sem empty. And now if we actually try to run this, we should get a result that's much better, in the sense that we no longer get skipped elements, as you might notice, but we also don't get negative ones, right? So both of these issues have been solved simply because of these semaphores, because these semaphores are gonna keep track of however many elements are in the buffer, and this sem wait is gonna wait until at least one is either in the state of being full, right? At least there is one when taken, or at least there is one slot empty when trying to produce and put one into the buffer, right? So therefore that means that we no longer need this if statement, because if we're here, right, sem empty necessarily needs to be at least 1. If sem empty is 1, that means that count is at least 9, right? So either 9 or lower. That means that at least one slot is free. That means that we don't need to check here. We don't need this else at all. We just need to execute this. And similarly here, because if we have sem weighted on sem full really represents the number, the count here. So because of that, sem full is actually going to represent the count, and it is going to be higher than 0 necessarily, otherwise sem weight would have blocked here. So this is always true. So we don't have to any longer check this. And in fact, we don't even need to assign it a -1 here, but yeah, we can remove it and it's probably going to be fine. So again, if we launch this, this is probably fine. So now we can play around a bit with this, since it should be able to work with as many consumers and as many producers we give it, right? So first things first, let's limit this this output, because it's quite really fast and we don't know if we have 4 times as many threads, it wouldn't make a difference. So let's say we sleep 1 second after every. So let's say the consumption itself takes 1 second, and then let's say that the producing an element takes in 1 second as well. If we try to launch this, we're gonna get 1 element a second. So that's kind of expected. That's fine. And the buffer is probably not even getting filled, right? Now, the interesting part is this should work even if the sleep 1 is only on one side. So if I remove the sleep 1 from the producer, let the producer create as fast as possible elements, it's still gonna print once a second and it shouldn't crash, simply because of those semaphores. So at one point, the buffer got filled and it started waiting on this a lot, right? So probably now it's actually filled up and it's just sem wait until the consumer takes in elements, right? And of course, if we have multiple threads, so let's say we up this number to 8, we should get, instead of just 1 a second, we should get 4 elements a second, which works nicely. And this should happen even if we take away the sleep time on our consumer, because even though the consumer could read as fast as possible, the producer would still just produce once a second. So it will be the same result. As you can see, just that these consumers are going to wait a lot more on the same wait. So this is a lot more efficient than actually just keep on checking every, I don't know how many milliseconds for that count to be whatever number, especially if you're dealing with mutexes. At that point, it's going to be quite costly in terms of CPU time. And this should also work the same even if we have just one consumer. So let's say that we have 8 threads and just the first one is a consumer, the rest are producers. So to do this, I'm going to change it here in main, in the create part of it. So here we have in the if being the producers, I'm going to say here if I is higher than 0, then create a producer, and if it's 0, then of course create a consumer. So it's going to only create one consumer, the rest are going to be producers, and in this case we're going to get 7 numbers a second, as you can see here, simply because the consumer can consume the elements from the buffer as fast as possible, but the producer is limited. So this is sort of the problems that the producer-consumer problem tries to solve, right? Whenever we have more producers than consumers, whenever we have more consumers than producers, whenever we have the producers producing more elements than the consumer can consume, and vice versa, and so on and so forth. All these issues need to be solved in this problem. And this is not the be-all end-all solution that I have presented to you here. There are better ones out there. There are more fit ones for the actual problem that you're trying to solve. But in our case, generally, this is good enough. But if you, for example, as I said, the producer, like the produce stage and the consume stage, if those don't take time at all, right, then that's a bit of a problem, because then it would mean that this part is what will take the most, right, adding it to the actual buffer, right? And because of that, it might be that due to the fact that it takes so much to add to the buffer, since it's a critical section, again, it can only be executed by one thread, we might have to optimize this so that multiple threads could actually write to this buffer at the same time. Okay, that's about it for this video. I hope you got something out of it. I hope you understood what this problem is about. I know it's a bit abstract, but trust me, if you look around, if you know about this problem and you look around a bit, you will find it at every corner. If you do have any questions, leave them down in comments below or on our Discord server. Again, the source code is going to be found down in the description below on our website. Take care. Bye.